countless generations, human beings have looked up at the stars, always asking the same question. Are we alone in the universe? Or is there something, or someone, watching us from the dark? The cosmos offers billions of chances for life to exist. Since the 1990s, when the first exoplanet was discovered, a planet orbiting a star other than the Sun, we've detected almost 6,000 worlds. Many of them are rocky planets with liquid water on their surface, similar to Earth. The problem is that distances in space are so enormous that, in practice, they almost completely rule out any kind of visit or contact, even if we could travel at the speed of light. But what if aliens were, in a way, our neighbors? What if they've been much closer all along than we ever imagined? Is Earth really the only place with life in the entire solar system? The answer might surprise you. On the outskirts of the region where the Sun moves, there are dozens of planetary bodies that could host some kind of life. Moons with oceans that hold far more liquid water than Earth and with intense geological activity. These places are potential cradles where life could arise and be sustained. Today, we're going to explore that idea, traveling through the solar system from the inside out, looking at which planets and moons are the most promising for life. That way, we can understand where and how it might thrive. These are the possible homes for life in the solar system. Megatelescopes like the James Webb are bringing us closer than ever to the possibility of confirming life on another planet. This might even be the instrument that detects the first aliens. This telescope, a true masterpiece of engineering, can detect extremely faint sources of heat. To do that, it has to operate at a temperature very close to absolute zero. That level of sensitivity is perfect, both for studying the early universe and its first galaxies, and for analyzing the atmospheres of distant planets in search of signs of life. It may sound odd, but we're not looking for little green men. We're looking for microscopic, single-celled organisms like bacteria. Even though they're tiny, they can completely transform a planet's atmosphere, filling it with gases that can't be produced by purely inorganic processes. Detecting this kind of compound in an exoplanet's atmosphere would be very strong evidence of biological activity. This kind of unicellular life could easily be the most common form of life in the universe. It's highly adaptable, evolves quickly, can draw energy from many different sources, and can survive in extreme conditions, just like extremophiles do on Earth. They hide in ice, in zones of high pressure and temperature, and can even withstand space radiation. That gives us hope of finding beings as small as they are tough, living on other worlds. Even so, visiting those exoplanets is impossible with our current technology. A mission like that would take, at the very least, tens of thousands of years. Until we learn how to manipulate space-time, long-distance observation will remain our best option for confirming the existence of life beyond Earth. From what we know today, out of all the bodies in the solar system, only Earth can sustain complex life that's visible to the naked eye. Animals, fungi, plants, and the many ecosystems they form together. When we talk about life in the universe and how to detect it, we have to lower our expectations a bit. The most likely thing we'll find is something far less spectacular than life on Earth today, which, during its first 4 billion years, was basically just a planet of bacteria. To begin with, defining what life is has been a problem that's puzzled philosophy and science for centuries. To this day, there's no single, clear, and precise definition. So how do we look for something we can't even fully describe? Are we really prepared to recognize every possible form of life and its signals? Probably not completely, but we've still started that search, and the first results are encouraging. For now, we're looking for beings capable of breathing, reproducing, changing their environment, evolving, and persisting over time through natural selection and other evolutionary processes. What we're trying to find is life as we know it. That is, life based on the chemistry we see on Earth. But there could also be life as we don't know it, based on strange chemistries, on planets and bodies that we wouldn't even consider habitable today. To make things even more complicated, we don't even know what most of the mass of the universe is made of. Everything we can see, stars, planets, ourselves, is made of what we call baryonic matter, the atoms and elements of the periodic table that interact chemically, electrically, and through gravity. However, that's not enough to explain the mass and gravity of many regions of the cosmos, or how galaxies move and form. That's why we talk about dark matter, a mysterious kind of matter, very hard to detect, that seems to concentrate in the centers of galaxies and only interacts with our kind of matter through gravity. If a person made of dark matter were standing in your room, you'd never know. You wouldn't see them, you couldn't touch them, and you couldn't interact with them in any way except through a tiny gravitational influence. It would be like a ghost universe superimposed on ours, warping space-time without leaving any other trace. We have no idea whether there are stars, planets, or even life forms made of dark matter. It's something completely outside our imagination. We may also be unaware of many possible forms of life in the universe, but at least we understand one example reasonably well: life on Earth. Life on Earth is one of nature's greatest shows. Enormous diversity and a very ancient history full of abrupt changes. Although we often picture our planet as a protective mother, some kind of Gaia, the reality is that Earth also poses many challenges and risks for habitability. Over Earth's history, there have been many times when life and the physical environment have collided in disastrous ways, causing catastrophes that almost wiped life out. The most famous are the planet's 5 great mass extinctions. That's exactly the opposite of what complex life, animals, plants, fungi, needs to thrive. And yet, life itself may be a product of the chaos in which planets are born. The cradle of life is probably young planets with oceans of hot, electrically charged water, full of organic molecules and energy, like Earth was in its early days. The Hadean, the era when our planet was forming, its first 500 million years, is the period we need to look at if we want to understand where and how life first emerged. It was a world completely uninhabitable for us, but it had everything needed to get started: water, energy, fats, amino acids, and nucleotides. As hot water passed through the pores in rocks carrying these components, thin films of phospholipids, fat molecules, formed, and thanks to their electrical properties, arranged themselves in a very particular way. The head of these molecules is attracted to water, while the tail repels it. That makes them group into layers and very often curve and close in on themselves, forming bubbles that grow and divide spontaneously, although they also break apart easily. These bubbles, called liposomes, are tiny microscopic droplets of fat. They may have been the very first step toward the plasma membrane, the structure that separates an organism from the outside world. That membrane allows molecules to concentrate inside, speeds up chemical reactions, and increases the chances that important interactions will take place in a protected environment. Back then, Earth acted like a gigantic battery. Acidic oceans at the surface and a more alkaline, rocky mantle inside. In undersea vents and volcanoes, the differences in electrical charge favored strange chemical reactions that may have helped form the basic building blocks of the first genomes and metabolites, the molecules used in metabolism. For the first 4 billion years, life on Earth was exclusively unicellular, despite all the transformations that took place during that time. We often call these long periods, informally, the age of bacteria. They include the Archean and Proterozoic eons. Throughout that entire stage, there was no kind of life visible to the naked eye on our planet. And it's precisely this type of simple, unicellular life that we expect to find most often in the universe. From what we understand, the conditions needed for this microscopic life to exist are far more common than those that allow complex multicellular life, which is much more fragile. On top of that, evolution is blind. It doesn't aim for complexity as a final goal. The transition from simple chemistry to biology was one of the strangest, most unlikely, and most decisive moments in all of history. Not just Earth's history, but the history of the entire universe. The truth is, many of us struggle to imagine that the same process that gave rise to life on Earth might also have taken place somewhere else in our own solar system. But the story of many of those worlds began in a very similar way to Earth's, and they may have offered, at some point, favorable conditions for life to appear. Venus and Mars, for example, haven't always been totally inhospitable. In the past, they had oceans, magnetic fields, and milder atmospheres. They were environments that fit quite well with what we would now call potentially habitable. Likewise, life could have arisen independently on several moons in the solar system, and might still be hiding in their deep, dark subsurface oceans. But there's an important detail. For life to exist on another planet, it doesn't necessarily have to have been born there. It might have arrived from somewhere else. This is where the panspermia hypothesis comes in. The idea that life can travel around the solar system riding on rocks. Even today, Earth still gets hit by meteorites that come from the Moon, from Mars, from the asteroid belt, and from other places. In the planet's early days, that bombardment was far more intense, almost daily. Very powerful impacts on Earth could have launched fragments of rock into space with microorganisms clinging to them. Those fragments might have ended up falling onto other planets and, with some luck, colonizing them. In that sense, Earth could have been like a loving but infectious relative. It hugs you and sprays life all over the neighborhood. However, all this means that if we ever find life somewhere else in the solar system, we'll have to ask a crucial question. Is that life form completely independent? Or is it just a very distant branch of our own tree of life? With these possibilities in mind, we can start our journey to study habitability in the solar system, beginning with one of its most important elements, the Sun, our parent star. The Sun is a middle-aged star in the main sequence, the longest stage in a star's life. It's not among the largest stars, but it is more massive than most stars in the universe. And unlike many stars in our galaxy, the Sun has no partner. It's a solitary star. Most stars form binary systems, where two stars orbit a common center of mass and can even share planets. On those worlds, the sky can have two suns. The fact that the Sun is the only star in the solar system makes the environment more stable and less chaotic, which favors habitability. It also helps a lot that the planet's orbits have very little eccentricity. They're almost circular. That reduces the gravitational disturbances between them and creates a calmer cosmic neighborhood in which planets and life can evolve. In most planetary systems, the planet's orbits are very eccentric or elongated, which generates strong perturbations and gravitational resonances among them. Sometimes this ends with planets being swallowed by their star or ejected from the system altogether. The first planet in the solar system, counting outward from the Sun, is Mercury. It's a rocky world, similar to the Moon, but much denser and with a highly metallic interior. Mercury is a planet of extremes. It circles dangerously close to the Sun, and its cratered surface bears the scars of billions of years of impacts. Its geology is almost completely shut down, and today it's a dry, desolate landscape. On top of that, temperatures on Mercury are brutal. During the day, the surface can exceed 420 degrees Celsius, hot enough to melt lead. At night, because it has almost no atmosphere, the heat escapes into space and the temperature drops to negative 170 degrees Celsius. Such extreme contrasts would be a huge problem for any kind of life. Mercury's thin exosphere doesn't retain heat or shield it from solar radiation. There's no liquid water and no breathable air. Everything suggests that the life chances are very low, but not absolutely zero. In some craters near the poles, in places where sunlight never reaches, scientists have found water ice protected from heat. These are tiny frozen deposits that act like hidden oases, reminding us that even in the most unlikely places, nature can still hold surprises. The second planet from the Sun is Venus, the brightest object in the night sky after the Moon. Unlike Mercury, Venus has a very dense atmosphere with a pressure about 90 times that of Earth's. This atmosphere wraps the planet in a layer of white golden clouds. They're clouds of highly corrosive sulfuric acid that reflect a lot of sunlight. A runaway greenhouse effect makes Venus the hottest planet in the solar system, with temperatures close to 500 degrees Celsius. Its rotation is also strange. It spins very slowly and in the opposite direction to most planets. On Venus, the sun rises in the west and sets in the east, and a single day lasts longer than a Venusian year. The sun's influence, or a huge impact in its youth, probably changed its spin completely. Venus is sometimes called Earth's sister planet because it's rocky, has a similar composition, and is almost the same size, about 98% of Earth's mass. However, for reasons we still don't fully understand, it doesn't have active tectonic plates constantly renewing its surface like Earth does, and that may have been key to it ending up as the hellish world we see today. Carl Sagan, one of the great scientists and science communicators of the 20th century, championed a very striking idea: that life could exist in the upper layers of Venus's clouds. High up, where pressure and temperature are similar to those on Earth, there might be microorganisms floating around, adapted to an environment rich in sulfuric acid and wrapped in thick clouds. For a long time, this was little more than a theoretical curiosity. But in September 2020, it came roaring back into the spotlight. An international team of scientists, led by Jane Greaves, announced that they had detected phosphine in Venus's atmosphere. Phosphine is a gas made of phosphorus and hydrogen and is considered a potential biosignature because, on Earth, it's produced mainly by microorganisms that live without oxygen or by certain industrial processes. If this finding is confirmed, the implications would be enormous. If the phosphine really comes from biological processes, it would mean that life can exist in extremely hostile environments, greatly expanding our idea of what counts as a habitable place. In that case, Venus, which we tend to think of as a dead planet, might host some very strange kind of ecosystem, adapted to conditions that currently seem impossible to us. The study is still highly debated, and many researchers are not convinced by the results. But if they turn out to be correct, there could be life as close as our neighboring planet, and we might have already detected it. The third planet in the solar system is Earth, which is both the largest and the strangest of the rocky planets. The first thing that stands out is that its surface isn't covered in craters, as you might expect from a world more than 4.6 billion years old. Instead, we see oceans and continents that constantly reshape the crust. This happens because, unlike any other planetary body we know, Earth's crust is broken into plates that move thanks to heat from the planet's interior. Over very long timescales, that movement allows parts of the oceans, continents, and atmosphere to be recycled, keeping the climate relatively stable for billions of years. That prevents the planet from spiraling into extreme states that would make life on the surface impossible, like what happened on Venus. The second standout feature, and a key factor in Earth's habitability, is its strong magnetic field. This invisible bubble protects the planet from many types of solar radiation that are harmful to life. The magnetosphere also stops the atmosphere and oceans from being slowly stripped away by the solar wind, that constant flow of charged particles emitted by the sun. Earth's magnetic field is generated by the movement of its second innermost layer, the outer core, made of liquid iron and nickel. It's like a metallic ocean at extremely high temperature and pressure, surrounding the inner core, a solid ball of iron and nickel about the size of the moon, with a temperature similar to the sun's surface. This internal heat, which keeps Earth's interior active and prevents the planet from dying geologically, has several main sources. First, the leftover heat from its formation, when Earth was built up from trillions of collisions between rocks and dust. Second, heat is produced by the radioactive decay of heavy elements concentrated in the core. And, finally, heat is generated by tidal friction and slight deformations of the planet caused by the moon's gravity. In fact, the formation of the moon itself was probably the result of great chaos, a gigantic impact between a protoplanet and the early Earth. This is the Theia hypothesis, which proposes that an object about the size of Mars slammed into Earth during its first few 100 million years. That collision would have produced even more heat, and the debris thrown into orbit would eventually have come together to form our satellite. The moon is a rarity in its own right, and may be one of the reasons Earth has remained habitable for so long. Although it's much smaller than our planet, it's one of the largest moons in the solar system, and relative to the size of its planet, the largest of all. It's not much smaller than Mercury. Its gravity has been crucial in keeping Earth's interior hot and moving, delaying its geological shutdown. Today, the moon is drifting away by a few centimeters per year and rotating ever more slowly. But for billions of years, it orbited much closer in a chaotic way, raising colossal tides and deforming Earth's interior with its gravitational pull. In a sense, the Earth-Moon system can almost be seen as a double-planet system. It's possible that without the moon, our magnetic field would have faded away billions of years ago. Without tectonic plates, without oceans of liquid water, without a dense atmosphere, and without a magnetic field, Earth might still have a few small habitable refuges. But it would never have developed the immense biomass and biodiversity of microscopic and multicellular life we see today. Then we have Mars, the fourth planet in the solar system, which has fascinated humanity for centuries. We call it the red planet because of its surface color, caused by iron oxides that coat it. It's a world full of extremes and mysteries. It's about half the size of Earth and has a very thin atmosphere, made mostly of carbon dioxide with small amounts of nitrogen and argon. This layer of air is so thin that it hardly shields the surface from solar and cosmic radiation, one of the biggest obstacles to Mars being habitable today. Mars's surface has spectacular geography. It hosts Olympus Mons, the largest volcano in the solar system, at about 20 kilometers high, and Valles Marineris, a canyon more than 4,000 kilometers long and up to 7 kilometers deep. Mars also has polar caps made of water ice and frozen carbon dioxide, which grow and shrink with the seasons. The presence of water is one of the most interesting aspects of the planet. Traces of ancient riverbeds, minerals that only form in the presence of water, and the possible existence of subsurface lakes all suggest that Mars was once a much wetter and probably habitable place. Today, the surface is very hostile to life as we know it. The atmosphere is extremely thin, and Mars has no global magnetic field, so solar and cosmic radiation hit almost unfiltered. That makes the environment very harsh for any living organism. Even so, the possibility remains that microbial life exists or once existed there, especially in sheltered locations. Underground aquifers where liquid water might persist, or high-pressure regions beneath permanent polar ice where radiation is weaker. The search for signs of life on Mars has been the goal of many robotic missions, from the Viking 1 and 2 landers in the 1970s to the current rovers Curiosity and Perseverance. We've been learning more and more about the planet. Curiosity, which landed in 2012, confirmed the presence of organic compounds and of conditions that could have allowed microbial life in the past. Perseverance, which arrived in 2021, is collecting rock samples that may contain signs of life, with the idea of bringing them back to Earth one day. They're essentially robotic paleontologists searching for evidence of past or present life on Mars. Continuing our journey outward through the solar system, we leave behind the rocky planets and arrive at the most massive gas giant, Jupiter. One of its most striking features is its atmosphere, very active and colorful, made of bands of clouds that race around the planet. It's composed mainly of hydrogen and helium, with small amounts of ammonia, methane, and water vapor. The famous Great Red Spot is a gigantic storm that has been raging for at least 400 years. It's a huge, high-pressure vortex with winds of up to 600 kilometers per hour, large enough to swallow Earth whole. Another impressive aspect of Jupiter is its magnetic field, the strongest of any planet in the solar system, about 20,000 times more intense than Earth's. This field produces spectacular auroras at its poles, which can be observed from Earth with powerful telescopes. On some of Jupiter's moons that are in the right positions, its powerful magnetic field can offer some protection from certain kinds of particles and radiation, making the environment somewhat more habitable. In others, that same field redirects charged particles that end up bombarding their surfaces. Jupiter also plays a vital role as a guardian of the inner solar system. Its enormous gravity attracts and deflects many comets and asteroids that might otherwise collide with planets like Earth. It was the first planet to form, a primordial giant that holds clues to the origin of the solar system. At the same time, it's almost like a miniature solar system of its own, with around 92 moons. Its 4 main moons, the Galilean moons, are full-fledged worlds: Io, volcanic and extremely active; Europa, icy and very promising for life; Ganymede, the largest moon in the solar system, with its own magnetic field; and Callisto, covered in craters that tell a long story of impacts. When it comes to habitability, the one that interests us most is Europa, one of the most fascinating bodies in the solar system. Data from missions like Galileo and observations with the Hubble telescope indicate that Europa has an ocean of liquid water beneath its icy crust. That ocean could be more than 100 kilometers deep and contain more water than all of Earth's oceans combined, which, on average, are only about 4 kilometers deep. A thin layer compared to Europa. The surface of this moon is covered by a shell of ice that may be anywhere from a few kilometers to several dozen kilometers thick. Cracks and strange patterns in the ice suggest that this shell is moving, probably because it's interacting with the ocean below. Hubble has also seen possible plumes of water vapor shooting into space, indicating a lot of activity beneath the ice. The main source of heat on Europa is tidal forces generated by Jupiter's gravity. Since its orbit is slightly elliptical, the moon is stretched and squeezed as it moves, producing heat through friction in its interior. This keeps the ocean liquid and makes Europa geologically active. The combination of liquid water, heat sources, and potentially essential chemical elements makes Europa one of the most promising places to search for life in the solar system. Its ocean could contain salts and organic compounds similar to those in Earth's oceans. Interactions between water and heat sources could release minerals and nutrients, creating an environment where life might emerge or survive. Several future missions are planned to study Europa in more detail and help us solve some of these big questions. Saturn, the sixth planet in the solar system, is a true cosmic gem, famous for its spectacular rings made mostly of ice and dust. It's a gas giant with an atmosphere composed mainly of hydrogen and helium. Its equatorial diameter is about 9 times that of Earth, and its density is so low that, in theory, it would float if you could put it in an ocean big enough. Saturn is home to very strong winds, up to 1,800 kilometers per hour, and a highly dynamic climate, with curiosities like a hexagon-shaped storm at one of its poles. Saturn also has more than 140 moons, all different from one another, and some of them might even be interesting places for life. But when we talk about habitability, one moon steals the spotlight. Titan, the second largest moon in the solar system, only slightly smaller than Ganymede. Titan is bigger than the planet Mercury and is the only moon in the solar system with a dense atmosphere, mainly made of nitrogen. It has a kind of hydrological cycle similar to Earth's, but instead of water, the liquid involved is methane. It's so cold that water behaves like rock, and if it were liquid, it would be almost like lava compared to Titan's environment. On Titan, there are lakes, rivers, rain, and even seas of liquid methane resting on a crust of ice. Below that crust, there may be a layer of liquid water mixed with ammonia. On Earth, hydrocarbons like methane are highly flammable gases, the kind of thing we burn in our stoves. But on Titan, since there's no oxygen in the atmosphere, those methane lakes don't catch fire. Titan is the only rocky body in the solar system, besides Earth, that has large quantities of liquid on its surface, forming landscapes that look surprisingly familiar. With those hydrocarbons, you could make plastics, fuels, building materials, and fertilizers. Water could be extracted from underground, and gaseous oxygen could be obtained by splitting water through electrolysis. In other words, at least in theory, the basics for a self-sufficient colony are all there. The combination of organic compounds, chemical energy, and a possible watery environment makes Titan one of the most interesting places to search for life in the solar system. Its atmosphere, with twice the pressure of Earth's and made of about 98% nitrogen, is the most similar to ours anywhere in the solar system. You wouldn't need a complicated pressurized suit to walk on the surface. Good thermal insulation to withstand minus 180 degrees Celsius, and an oxygen system would do. In terms of difficulty, it wouldn't be that different from walking in Antarctica in winter. That's why many people see Titan as one of the best candidates for a future human colony. And unlike Mars, Titan is well shielded from the most harmful radiation thanks to Saturn's magnetic field and its thick atmosphere. Despite having such a dense atmosphere, its gravity is only about 15% of Earth's, which means that with the right equipment, flying there would be almost as easy as swimming. Maybe one day our descendants will fly through those skies and play beneath methane waterfalls. Titan is by far Saturn's largest moon and one of the most mysterious in the entire solar system. But besides Titan, Saturn has other very interesting moons that might also harbor life, especially in oceans of liquid water hidden beneath their icy surfaces. The most notable are Enceladus and Mimas. Enceladus is a small moon, only about 500 kilometers in diameter. NASA's Cassini spacecraft discovered that it has a global ocean of liquid water beneath its ice shell, heated by geothermal activity at the sea floor. Part of that ocean escapes into space as enormous geysers at the South Pole, shooting out water vapor, ice, and organic compounds. Cassini also detected molecular hydrogen in these plumes, suggesting the presence of hydrothermal vents on the sea floor, very similar to the ones we see on Earth, where life thrives without any need for sunlight. The combination of liquid water, organic compounds, and chemical energy makes Enceladus a very serious candidate for hosting microbial life. Mimas, on the other hand, has surprised scientists. It's famous for its appearance, which resembles the Death Star from Star Wars because of its enormous Herschel crater, one of the largest in the solar system. For a long time, Mimas was thought to be a completely dead world, geologically speaking. However, recent studies using Cassini data suggest that it might also have an ocean beneath its surface. This possible ocean was inferred by analyzing how Mimas wobbles in its orbit. That motion fits with an interior that contains liquid water under an ice shell 20 to 30 kilometers thick. If confirmed, Mimas would join the club of ocean worlds in the solar system, expanding the list of places where life might find refuge in locations we never would have considered. These moons, Enceladus, Mimas, Titan, and other icy moons, show that life could arise in extreme environments, far from sunlight, as long as there's liquid water, a source of energy, and the right chemical ingredients. Farther out still, we find Uranus and Neptune, the solar system's ice giants, two distant, enigmatic worlds that are sometimes described as cosmic siblings. Uranus, the seventh planet from the Sun, is especially odd. Its most striking feature is that its axis of rotation is extremely tilted, about 98 degrees relative to its orbit. That makes Uranus look like it's rolling around the Sun on its side, as if it were lying down while spinning. This extreme tilt gives Uranus incredibly long seasons. Each pole spends about 42 years in constant sunlight and then 42 years in complete darkness. Uranus has a relatively small rocky core surrounded by a layer of water, ammonia, and methane in liquid form. Its atmosphere is very cold, with average temperatures around -224 degrees Celsius, making it the coldest planet in the solar system. Neptune, the eighth and most distant planet from the Sun, is also an extreme world. Its atmosphere is dominated by incredibly fast winds that can reach 2,100 kilometers per hour, the fastest in the solar system. Those winds are powered by the planet's internal heat, as Neptune radiates more energy than it receives from the Sun. Like Uranus, Neptune has a deep blue color due to methane in its atmosphere. However, it appears darker and shows large atmospheric structures such as the Great Dark Spot, a huge storm similar in concept to Jupiter's Great Red Spot. Both Uranus and Neptune are called ice giants because they contain large amounts of water, ammonia, and methane in solid or liquid form, in addition to the gases in their atmospheres. Each of these planets has moons that are of great scientific interest, especially when we talk about habitability. Uranus has 27 known moons, and Neptune has 14, of which Triton is the most important. Triton, Neptune's largest moon, is a very intriguing world. It has an icy surface and active geysers that eject nitrogen, showing that it's geologically active. It may hide a subsurface ocean of liquid water kept warm by tidal heating due to Neptune's gravity. Among Uranus's moons, Miranda stands out for its strange, chaotic surface, full of huge faults and canyons that point to a violent geological past. For now, none of Uranus's moons is considered clearly habitable, but it's still possible that some of them contain water in solid form or even liquid water in their interiors. As we've seen, some worlds contain liquid water and could give rise to or sustain life in deep, warm, active interior oceans far from the Sun, at the limits of the solar system. On these icy moons, needed by the gravity and geological activity of the giant planets they orbit, life might have found the heat and energy it needs to thrive. And that's only the beginning. There may be dwarf planets and other bodies beyond the orbit of Pluto that, although very difficult to explore, could also support some kind of life. But for now, we end this journey almost 5 billion kilometers from the Sun, with the feeling that our cosmic neighborhood is full of potential hiding places for life. Maybe biology really is exclusive to Earth. Or maybe it exists in other corners of the solar system. In any case, we've never been closer to finding out. Thank you very much for making it this far. If you're not subscribed yet, consider subscribing and sharing this video with a friend. See you next time.